So this is a chapter on different types of stars and what we know about stars, and we'll look at things like the Hertzsprung-Russell diagrams, sort of how do we catalog stars. So the first discussion is really on what we can see with our naked eye. You can see about 6,000 stars from Earth. Stars vary in luminosity a lot. It turns out stars that you see with your naked eye are generally not typical because some stars are so much brighter than others. The star Betelgeuse in the constellation Orion has the luminosity of about 10,000 suns. That's the wattage, 10,000 times the luminosity of sun. So you'd have to have 10,000 suns next to each other to be as bright as Betelgeuse is, which means you could still see it if it was 100 times farther away than the sun is. And so bright stars are the ones that are easiest to see, and those are the ones we see in our sky, typically. Those also, for the most part, tend to be the most massive stars. So we can look at a picture. What's interesting about this picture is this is the Small Magellanic Cloud. So these are stars taken in a different galaxy, a nearby galaxy, but not the Milky Way. And so all the stars, since they're all in that galaxy, are at about the same distance, and you can see they come in different sizes and colors, roughly speaking. And so there's a lot of variety in stars. We'll be talking about that and how we know what we know as we go. Here's a picture of the sun's neighborhood. And so in this picture, we can sort of look at the caption here a little bit. You see all these little all the circled ones are brown dwarfs. So here's the sun. It's sort of a whitish star, or a yellow star. All the ones that are red or circled are cooler and smaller than the sun. And so you see so many more of those than you see of bright stars. And it turns out that there are lots more low-mass stars than high-mass stars, and that stands to reason because stars form in clouds of dust, and so it's easier to make small ones than large ones. And since there's a lot of mass available, lots of stars get made, and so many more small ones are around than large ones. And so even though we preferentially see the bright ones, there are many, many small ones. The sun is somewhere in the middle of all of that. Ooh, I got off my chart. Okay. So that's the distribution of stellar masses. There are many more small mass stars than large mass stars. Stars form from clouds of gas. As a result, many small ones form. There's just more available. When the stuff starts collapsing, it's easier to make something small than something big. Rigel, a star in the constellation Orion, sort of the opposite corner of Orion's body from Betelgeuse that we were just talking about, is about 20 times the mass of the sun. Rigel's luminosity is about 100 times that of the sun, and so it'll have a much shorter life. If you have a higher luminosity, your luminosity is the rate at which you're burning fuel. And so if you're burning fuel faster than the guy next to you, you burn yours up faster. And so even though it's 20 times more massive, it's burning 100 times faster. And so its lifetime will be 5 times as short. It'll actually be less than that. It'll be even smaller than that. But you just saw Betelgeuse is burning its fuel at 10,000 times the rate the sun is. And so as a result, it'll run out of fuel much, much faster than the sun will. So here's a population count, sort of. Remember, we talked about O, B, A, F, G, K, M for the spectral types. O's were the hottest and M's were the coolest, right? So within 21 light years of the sun, so just in our little neighborhood, you might say, there are 2 A stars, 1 F star, 7 G stars, 17 K stars, and 94 M stars. So that's a nice measure of how many low-mass stars there are. 33 brown dwarfs and 8 white dwarfs. Remember, white dwarfs are stars that are sort of at the end of their lives. Okay, let me just do this. So how do we measure stellar masses? This is a tricky business. We measure stellar masses by observing binary star systems. You can think of trying to figure out masses as putting things on a seesaw or a balance and seeing how they balance. And it turns out that if you watch 2 stars orbiting each other, you can use Newton's laws and determine their masses. And so we look at binary stars. There are three types of double stars, of binary systems. I guess I should say double stars. An optical double is two stars that just appear to be near each other because they're along the same line of sight, but they're not necessarily, one could be much farther away. You'd almost call that an optical illusion. That's why it's called an optical double. A visual binary is two stars that are orbiting each other that can be seen as two stars. I'll modify that in just a second. So if you look at it through a telescope or maybe with your naked eye, you see two stars near each other, and they're orbiting each other. And so that's called a visual binary. A spectroscopic binary is two stars that are so close together that they look at like one star to you, but you can look at their spectrum and watch it and see that they're actually two stars. And so I'll give you a version, a look at that here. So we looked at that one. These are some nearby stars. These are Alpha Centauri, sort of the nearest star cluster to us. And this little arrow down here is Proxima Centauri. Can you see a little, oops. Oh, dang it. You should be able to see a little arrow right here. That's Proxima Centauri. You know, it's a dim star. I think it's an M-type star. Yeah, it's an M-type star. And so it's very dim. And those stars you're seeing throughout this picture here on the right are all stars that are farther away. Right there is Proxima Centauri, and they had to expose enough light because it's so dim that all the background stars showed up also. So here's an example of two stars that are orbiting each other, and we can look at the time it takes them to do this little dance that they do, and see that they're obeying Newton's law. So this is what's happening in the center here. I don't know if you can see that, and that's how it looks going around the outside. And so as they orbit each other, we can apply Newton's version of Kepler's third law, and determine their masses. It's sort of like this. You know, it's just like kind of like a seesaw. The star that has the most mass will move the least when they orbit each other. And so what you'll see is one star making a bigger circle and the other star making a smaller circle. So here's a spectroscopic double, right? That was a visual binary. Here's a spectroscopic binary. So these stars, if you imagine that they're so close together that you can't separate them with your eye, right? Then all you're seeing is a spectrum of them. But if you're looking from down here, then in picture one up at the top, B is moving away and A is moving towards you. And so B's absorption spectrum will be red shifted and A's will be blue shifted. When they're moving laterally to your view, again, you're viewing from the bottom of the page, right, somewhere way down this way, they won't be shifted at all, so they'll have the same spectrum. Then when A is moving away and B is moving towards, they'll flip, and they'll be back. And so if you look at the spectrum over time, you'll see that something's weird's happening with it. It's two overlapping spectra, and so this is how we find visual doubles. Spectroscopic doubles is we look at the spectrum, and by watching the spectrum over time, we can see that the absorption lines are moving back and forth as they blue shift and red shift while they're orbiting each other. So we did visual binaries, those where you can just look with your eye and see that they're two stars, and we did spectroscopic binaries. That's down here. And so this is the formula, but you really just use, if I ask you about it, it'll be Newton's version of Kepler's third law. This is a relationship between the diameter of the orbit cubed is equal to the period squared times the masses. And this is, if you remember Kepler's third law, it says that the square of the period is proportional to the cube of the semi-major axis. And so this is basically Newton's version of Kepler's law. So it turns out that you can study the luminosities of stars. And the luminosity, which is in this graph on the y-axis, versus the mass on the left axis, if you just plot stars on there, what you notice is there's sort of like a straight line correlation here. And it turns out what this gives is the luminosity is proportional to the mass to the fourth power. And so that means if a star's mass is 10 times bigger, star B is 10 times more massive than star A, then star B's luminosity is 10 times 10 times 10 times 10, or 10,000 times bigger than star A's. So, for example, if you look at across the graph here, and let's look at a star with one, this is the masses are in solar masses. So a star with one solar mass, if I go straight up and then across, has a luminosity of about 1. One solar mass gives you about 1 solar luminosity. Now let's look at a star with 10 solar masses. Here's 10 solar masses. I get up to here somewhere. That's about 10,000 times the solar luminosities. So a factor of 10 in mass gives you a factor of 10,000 in luminosity. And so that's what this little formula is saying. The luminosity is determined by the mass. That is to say, how bright a star burns, right? What its total wattage is determined by its mass, and it's very sensitive to its mass. It's mass to the fourth power. And so that's a huge dependence on the mass. And so stars with really big mass have really high luminosities, and so they live really short lives. Big, bright stars live really short lives. Okay, so by the way, roughly speaking, solar masses go from about 1/12 of the sun's mass to about 250 solar masses. That M with a little circle there means a solar mass. Anytime you see a little circle with a dot in the middle, that represents the sun. So diameters of stars. How do we find out diameters of stars? Well, generally this is done by looking at what we call eclipsing binaries. So I'm going to go back to the other sheet here for a second and look at some stuff here. So that was more on those guys. Here's our chart. So this is a pair of stars. One's big and one's small, but they can be any kind of pair. And they're eclipsing binaries. That is to say, when you look at it from where we're looking, one passes behind the other. This wouldn't work if one of the stars was just going around as we were looking. So this wouldn't work if the star was, if the blue star was going around this way. You want it to be eclipsing binary, so sometimes it's in front and sometimes it's in back. What happens then is there are times where, like let's say at positions 1 and 3, both stars are shining, right? And so the brightness is up at its maximum value at 1 and 3. It's up here somewhere. Now let's look at position 2. In position 2, star 1, the blue star has passed behind the red star. And so we no longer get that light. All we get is just the light from the red star. And so as a result, the brightness that we see of the pair of them drops down. This distance it drops down is the brightness of the blue star, right? Then as the blue star comes out the other side, once again, we're back up to here. We're kind of in position 3. And then as we go into position 4, now you can still see most of the red star, but some of its brightness is covered by the blue star. And yet we see the brightness of the blue star. And so it only drops a little bit there. But you can use these to determine what fraction of one star is being blocked. And it allows you to figure out the relative sizes of the two diameters. Let me see. Here's a little more sophisticated view. You can see as I go from position 1 to position 2, the blue star slowly begins to block out some of the light from the red star, and so the brightness goes down. The blue star is completely visible in this region, but not all of the red star is visible, and so the total brightness is down. As it comes back out the other side, the brightness goes back up, and I can use these to determine the shape, the size of the blue star and the red star. I'm not going to go into the math of that equation. So let's talk about the Hertzsprung-Russell diagrams. So there are two guys, I think I wrote their names down somewhere, but maybe I didn't. Yeah, two astronomers named, one is a Danish guy named Ejnar Hertzsprung, and Henry Norris Russell, an American astronomer. I'm pretty sure he was the guy who Cecilia Payne's Nobel Prize. So what they did was they made a plot of stars where they graphed, instead of luminosity versus mass, they graphed luminosity versus temperature. Remember, graphing versus temperature is the same thing as graphing versus color or spectral type. Those basically are the same information. This plot is named after them, and it's called an HR diagram. And so let me just give you an example of one. So here's an HR diagram. This is just out of your PowerPoint. I just stuck it in. And so let's just talk about it for a second. So the luminosity is on this side. Notice the luminosity increases by powers of 10. So down here it doesn't have the number, but this would be a 1/1,000,000th, 10 to the minus 6. This is a 10,000th. This is a 100th. This is 1. This is 100. This is 1,000. This is 10,000. This is 1,000,000. So each one of these lines increases by a factor of 100. This is 1,000,000th. This is a 10,000th. This is 100th. This is 1. This is 100. This is 10,000. This is 1,000,000. Across the bottom axis, it's a little different. If we think in terms of temperature, temperature is increasing to the left. Look at that. Here's 3,000, 6,000, 10,000, 25,000, also kind of a log scale. Or you can look at the spectral classes where these are the red ones, the M's, and these are the O's, or you can think of color. That's what we were saying. So the temperature, the spectral class, and the color all give the sort of the same information. It goes from red, the cooler stars, to blue. So what these guys did was they just plotted all the stars they could observe, these ones that Andy Jump Cannon cataloged, and they plotted them, their luminosity versus spectral class or temperature or color on the x-axis. And what they found was really interesting. A lot of the stars just fell right along this axis. These are a lot of stars we see. Rigel, we talked about. Spica is up in the summertime. Rigel is mostly up in the winter. Vega is a summer star. Sirius is more of a winter star. Procyon is also sort of a winter star. Here's the sun. Here's Alpha Centauri. That's the one we're looking at a minute ago. It's very near the sun. Tau Ceti. This is Barnard's star. This is one the other day we were looking at that was moving very high speed laterally. Proxima Centauri is a star that's very near us. And you can see they sort of, from the lower right to the upper left, the stars fall along this sort of this path, which isn't quite a straight line, but we usually pretend that it is. And this is called the main sequence. Stars spend about 90% of their time on this main sequence. Up here, we have super bright giant stars. And down here, we have these giants are cool, right? They're at the right side of the graph, so they're in the cooler temperature range, but they're super luminous, which means they have to be really big. Because if you're going to be very luminous, if you're going to give off a lot of light, and you're not very hot, you have to be really big. So these stars up in this region are really big. They're called giants and supergiants. The stars in the lower left, these guys are hot, but they're not very luminous, so they must be very small. And so these are called dwarfs. So these are called giants and dwarfs, and along the middle of that diagonal line is the main sequence. So on the main sequence, luminosity increases as you move up into the left, right? So does mass, right? Remember, mass is, luminosity goes as mass to the fourth power, so these stars on the main sequence that are massive, are more luminous, are more massive also. Size increases from the lower left to the upper right. These are the really big stars in the upper right. These are the really small stars in the lower left. Let me see if I've got all that on there. So the diagonal band that goes from the lower right to the upper left is called the main sequence. It contains about 90% of stars. Stars fall on the main sequence while they are fusing hydrogen to helium. Before that and after that, they're elsewhere on the diagram. And so the main sequence, again, is the stars that are fusing hydrogen to helium. That's what stars do for most of their lifetime. In fact, for about 90% of their lifetime on average. Stars above the main sequence and to the right are more luminous but cooler. That's what we were just talking about. In order to be cooler and still produce more light, these stars have to be much larger. They're called giants and supergiants. Arcturus and the constellation Bootes, that's up right now, or at least in the summer. is a giant, but Betelgeuse, a winter star, and of the Orion constellation, and Antares, which is a summer star, are supergiants. Betelgeuse burns with a luminosity of 10,000 suns. Antares burns with a luminosity of 65,000 suns. So it's extremely luminous. Stars in the lower left are hotter and less luminous than their main sequence counterparts. In order for a star to be hotter and less luminous, it has to be smaller, as we were just saying. Both the giant and dwarf stages, that is to say the upper right and the lower left of the HR diagram, come afterwards. Stars move off the main sequence to the upper right, and then they circle around and end up in the lower left. A white dwarf can have a density of 100,000 times the density of the sun. The white dwarfs at the very end of the sun's life, it'll end up as a white dwarf. These objects have roughly the mass of the sun inside something the size of the Earth. And so a white dwarf can have a density more than 100,000 times the density of the sun. What I'm saying up here, I kind of have a typo there, but it's kind of funny. There are stages it should say the lives, not the loves, of certain stars with densities even greater than a white dwarf. There are things called neutron stars and black holes, which make neutron stars which make white dwarfs seem not very dense. So here's just a table of some relevant parameters, right? These are O-type stars, 40 solar masses, 700,000 times the luminosity of the sun, 40,000 Kelvin temperature, and a radius of 18 solar radii, and so on. You work your way down. Notice how much 40 times the mass, but 700,000 times the luminosity. The luminosity is extremely sensitive to the mass. Higher mass, higher luminosity, much higher luminosity. Okay, I think that's it.